Hi everyone. Welcome to the tutorial on logic programming. We have more people registered, but I guess we just start. People get here, and it's my pleasure to come here with my friends Marcello and Enrico. So we three very excited to give this tutorial, and we are also a little bit scary because I think I don't know how many of you have heard about logic programming before. Oh, okay, then all of us, right? So that is better. That's a better feeling now, and I think so. Before we really start. I would like to give you a kind of like a roadmap of the tutorial. So because it's like 3 hours long, so you may want to go out when it. So first we will introduce different flavors of logic programming to you. The first one is answer set programming. I'll cover that. Then constraint logic programming, and Enrico will cover that. And then constraint answer set programming. Marcello is going to talk about that. And we will have, because since this tutorial is geared towards the planning community, so we will need a representation language to talk about. So we'll talk a little bit about reasoning about action and chain, and we will talk about specifically about the action language B, that it is. So it has almost comparable with PDDL. And then we'll focus. So this is the main thing of this section of this tutorial. How do we plan using answer set programming in constraint logic programming with this technology? And then we describe a few applications, and depending on the time that we have left, so we'll go from top to bottom like that. And if we have more time, we prepare the slide, but we do not show here. So we also can show you how we use the logic programming technology in multi-agent domains as well. Okay, so that's the start. So now let us begin with some background on answer set programming. For the answer set programming, it really, by now it is not really new anymore, but it is almost just 20 years old. So it was introduced in the late 90s and managed to get a lot of attention from many other communities. Basically, the idea is that it is declarative, so you solve the problem by represent the problem rather than by developing algorithm for that, specific algorithm. And then the program can be developed incrementally. So you write the program to get certain type of answer. If you don't like that, or if you want to specialize the answer to a certain direction, you can add some more rules to that. And it's actually fairly expressive because it can solve problem with like sigma 2p and pi 2p complexity. And then the good thing about answer set programming lately is that it's there is like very a lot of research going on extending the language, the syntactic feature of the language that makes the representation of problem much easier. For example, like aggregates or something like that. Or so there are a whole research community focusing on developing the solver, so that I have no experience on developing the solver. I just take it and use it. That, and it has a lot of like applications. We'll go through some of this one. So to start, so the basic. I'm going to talk about answer set programming now. And the syntax of the language is very simple. So we have rules of the form like B1 or this is written or BM until, so this is the head, and then the body of the is A1 to AN and node AN plus 1 to node AN plus K. And where this AI and this BJ are atom of certain language is either propositional or first order. And this note is a special operator. This like default negation is standard. So and the language could be allowed. So it's not just only atoms, but classical negation it allows too. So, but there are at least two different ways of looking at a rule like this. The first rule saying that if this A1 to AN are true and none of these can be proven to be true, then at least one of these must be true. Okay, but there's also another one that is very similar to that, but that shows something that it lead to the different kind of thinking. So this one is if A1 to AN is believed to be true, and there's no reason to believe that any of this one is to be true, then at least one of that must be true. So you basically have rule of the form. And I think that so in here basically we go that this is the head and this is the body, and the idea is that if the body is true, then the head must be true. Okay? So we have special case like this. So this part can be empty, this part can be empty, and so if this part is empty, this represents a fact that must be true. And this one, so if this part is empty, that it represents a constraint. Okay. So a program is in general a set of rules. We have a set of rules, and I think this is basically the very standard notation in first order logic about Herbrand universe, Herbrand base, and rule with variables in logic program. It's are seen as like basically collection of ground rules that it's when we ground that with the Herbrand universe. Okay, so from now on we're just basically talking about ground rules, ground programs. So we have something like here. I just put up some of the example of like the program here. So if we have a set of propositions like this PQR, so we have this is a program, this program. So in all of these rules, all of its rule, there is no negation, no default negation. So this is a positive program. So this is a kind of like the program with default as negations, things like that. And we can have something like we have this standard program like this. So we can have something like all that. So to define the semantics of a general logic program, we go with two steps. First, we define the semantic of a positive propositions program. So basically, in this, there are not default negations. And so all of the rule of this form, so we can define a operator called like TP operators. That is, so to say that if we are given a set of atom X, then we will conclude all the A such that basically the body is belonging to this set. And we can show that this, of course, every fact of the program would belong to this, and it is a monotonic operators, and so we can basically convert to a fixed point, and and this is the fixed point that we're going to define. If we have a positive program, that the least fixed point of these TP operators is basically represent the semantic meaning of the program. So here's a few examples. Like we have this program. In the first step, we get A and C because they are the facts, and then we get, if we have A and C, we get B, and then we can know. So we get that. And I skip this example. That's very standard. So if we have program with variables, we will just define basically the semantic of the ground program. So I'm putting here that for the sake of, for the completeness of the presentation, but I'm not planning to go over that. So here, for example, let's look at this example. We have this P of F of X and P of X. So and if we have the language with like this one A and B, two functional symbol A and B, two constant and one function symbol. So we have like the grounding would be just become infinite. That's. And then we have like we can define the set of ground rules of the program like that. So I skip this one. For that, to define the semantic of a program with variable, we can also have a. So we have the Herbrand universe and Herbrand base defined like that, and we define the Herbrand interpretation, basically a collection of atoms in the Herbrand base. And we can define the least Herbrand model of the program. It basically it defines a model of the program is satisfying all the rules if, say for example, if this rule, if we have the interpretation I, then it will satisfy the rule, or it is a model of the rule if whenever the body is true, then the head must be true. Okay? So that, and basically one can show that this minimal Herbrand model is actually the result of the TP operator for positive program. So here is another example of how we calculate this TP operator and then the minimal Herbrand model of that. What we can show is that for every positive program pi with so we have yes.
Sarah.d.aaron@gmail.com is connecting.
Oh, she is connecting.
Oh, okay, that's fine. And now we will, if we have constraints, so what would be the semantic of the program? So we would define. What we would do is that we define. If we have a program pi and the set of atom x, we calculate this pi to the x. This is what it called the basically the reduction of pi with respect to x by doing two things. One, we remove all the rules that contain one of the atom in the default negation. So if we have a rule like this, and one of these element, one of these atom an plus 1 to an plus k here belong to x, then we remove that rules. And then we remove all of the remaining default negation atom from the remaining program. So in that case, after these two steps, we get a positive program. And the positive, so and then we can use the so we will say that basically a set of atom x equals the answer set of the program pi if x is the minimum model of this program pi of x. So you can see that if I have a set of atom x, I can easily check whether it is an answer set or not. Right? So that, and that's so and here say for we assuming that we have these two programs, this pi 2, this program A. So you can see that if I take S1, the reduct would be this one because none of these belong to S1. So and the minimum model of that program is this one. This is different. So this one is not an answer set. On the other hand, if we take S2 equal A, so when we do the reduct, we remove this rule, and then after that we remove this part. So we have A here. So and then this the minimum model of this program is at A. So this equal, and then we have an answer set, and so we go. So that's how we. And as you can see here that a program may have more than one models, one answer set, and if easily we can check that a program may have no answer set at all. So there are quite a number of interesting properties of an answer set. But so first of all, it is saying that if we have basically each of the elements in an answer set must be supported by the answer set. Basically, that's the idea of that. And then it is not redundant. So if you have in a set of atoms where you don't have anything, any rule that support that conclusion, you cannot do that. So that's basically the idea of the intuition behind the answer set semantic. I'm not going to go over all this. I'll give you an example. So for example, take this program. intuitively we have this program. If we look at this, previously we see that there are two possible answer sets, either A is true or B is true. But if A is true, then P must be true, but B is true. So then, if we take this one, and this set, empty set, and we have this one, then this set, we have this part, it's, so node B is not belong to this one, therefore A must be belong to that answer set, and therefore this one is not an answer set. On the other hand, the whole thing here, for example, oh, I have this one. If we have this set, then if A equals this, but the only rule that in this program is this one. But because B is in there, so we should not have that one. So this one is not an answer set either. So basically, with that we have the notion of an answer set of program. But so far we do not talk about the constraints. So how do we do with the constraint? So it's very simple. So first of all, we will collect all the constraints of the program and make it a set of pi of C, like that. And then we define that if we have a set of atoms, that is an answer set of the program without constraint. And then it has to satisfy all the constraints in this program. That's all that is. And what does it mean satisfied? When a constraint like that, it means that either one of these have to be false or that one of those is true in the answer set. Then the constraint is satisfied. So, and we have this, so there are many answer set solvers that implement, that compute the answer set. And one of those is Clink, for example, and you can download them from this website. And there is a very extensive documentation for that. And you can do that. If you have this program, you can calculate zero, you can calculate at least one or all of the answer set. So it's a little, I believe it's more advanced than the SAS solver, because if you use the SAS solver, you want to compute all models, you have to do something extra in order to do that. So here you just need to have. And so that how do we use this? So that basically, so far I give you the background on logic programming, the main notion of answer set. So how do we use logic programming under the answer set semantic to solve problem? So, and that's so the general idea of the answer set problem. So if we have a problem that we wanted to solve, traditional approach, okay, we develop algorithm to solve that, and implemented it, get the solution. How do we solve that using logic programming? Basically, we go through the modeling path. Like, we will represent the problem as a logic program. And then we use a solver, whether we use a Clink or whether we use anything that compute it answer set, and so and then we reinterpret that as a solution. The only catch here that we need to do this part so that each of these answer set corresponding to each of the solution here. There is a one-to-one corresponding between the solution and the answer set. I will demonstrate the use of that in using two examples here. So we all know the graph coloring problem, right? I will show you how this problem can be solved using logic program. And so we have this, with assuming that we have the graph G, and its node, it represents node from 1 to n, and then there are h between I and j that represent as a fact of the program. So what we'll do is that we will represent the problem as logic program. So now, in general, there are two parts. So first, what are the possible ways to get a solution? So because I need to assign each of the node one color, so I can write something like this. The color, if I have a node x, and its color is not assigned the blue or yellow, then it must be red, right? And then it is blue if it's not red and not yellow, and so on and so forth. So with these three rules, I will manage to assign each node one color, one and one only, right? And then I say, okay, there is a constraint that state that two nodes on the same edge cannot have the same color. So I just added the constraint. If I have the edge between x and y, so the color of x and the color of y have to be different. And the way we write is that if they are the same, then that is the constraint. So this is not acceptable. Okay? Right? So and then we can, so this is how, so say for example, we can have this. So that's how it, in order to run with the answer set, so variable need to be quantified. So we need to add the node x here to make sure that the variable here is instantiated with that. But that's, and we can easily show that if we have a graph G and we have the program P of G state in this way, each of the answer set would correspond to one solution and vice versa. And if the program doesn't have an answer set, that means that the problem is not solvable. So there are so now I will introduce to you some of the syntactic extension of logic programs that make life much easier when we wanted to solve problems using logic program. So here it's the first thing that that it was introduced what they call choice atoms. So choice atoms have this form. So here we have like P1 to P2 to Pk, and this is lower bound and this upper bound. That's saying that among all the atoms belonging to this set, at least this number of atoms has to be true, and at most this number have to be true. So then I can just write color of x. See, so for each node x, I should have exactly one of them in this set. So that's how it is. And so and the other one is weight atom. So the second type of extension is weight atom. So weight atom has, so it's similar to choice atom, but now we extended to have the weight of the atom here. So and basically the sum of the weight of all the atoms it's in this have to be bound by this lower and upper bound. Okay. And then there are also aggregate, like sum of the sum, the count. This one is, say for example, the sum of all the x such that P of A or the count of this one. And I should note that all of these extensions have been implemented in the most like in the state of the art solver. So if we wanted to use them, we can use them very effectively. And I will bother you with one more example of like how to solve the n-queen problem with like answer sets, which is very simple. Like here we have this basically we have the representation. We have like, okay, cell ij to represent the board, and then for each of solution we have like this value is true if we have one queen at that point and zero otherwise. And to generate a possible solution, we just need to say each of these could be either true or false, and then we just have that the checking to ensure that no queen attack each other. And how we do? So this is very simple. So we have the column, we have the row, and then here we generate a possible solution, and we can say that no two queens on the same row is like this, no two queens on the same column is like this, and then no two queens on the same diagonal. That's how we solve the problem. So, and I think that it's going to be Enrico.
Okay, so let's shift gear a little bit. Let's talk about constraint logic programming. So let me actually first of all make a connection between constraint logic programming and what Son has been talking so far, which is answer set programming. Answer set programming is what the logic programming community has embraced as the paradigm of choice at this point. Nevertheless, if we talk about logic programming outside of the logic programming community, a name that typically comes out is Prolog. So for many, many years, Prolog was logic programming, was the core. So what is the connection between Prolog and answer set programming? Essentially, the foundations are the same. Prolog is positive programs. And remember positive programs that Son has introduced just a moment ago. There is an important property of positive programs, the fact that you are guaranteed that there is only one answer set, one and exact one. So for this reason, when we write programs in Prolog, we don't write them in the same way as answer set programming. We don't use the models as representative of the solutions because we know there is only one model. So instead what we do, we actually pose queries. We ask questions, we interrogate the content of that unique model. So that's why very often when you write Prolog program, you see things like this, which is, I'm asking you a question, which is P of X. So what I'm trying to learn what are the values of P of X that are present in that unique model represented by the Prolog program. Now, Prolog programs, answer set programs, we have a syntax, we have a language, we have function symbols, we have predicate symbols. Now, all these components are uninterpreted. So for example, when I write something like this in Prolog, x equals square of 2, that square of 2 is nothing else than just a collection of symbols. They don't have any meaning attached to it, which means if I give a query, if I have this rule in my program and I give a query, tell me for which value of x, P of X is true, I'm going to get back x equals square of 2 and don't get 4. Because Prolog doesn't know that square of 2 should be computed as 4. And of course, if we actually write things like these, I'm asking the question to Prolog, is 3 equal to 2 plus 1? I'm getting no, because 3 is syntactically not the same as 2 plus 1. Or if I take a variable here, there is no way I'm going to get a value for that variable because, again, we're trying to make things syntactically equal. Prolog uses unification to actually compare things. Now, Prolog, of course, realized from the beginning that this was an issue. We want to be able to use numbers, so they started introducing some special predicate, like, for example, is, which is nothing else than something that forces evaluation of arithmetic expressions. But it's an extra logical thing. It doesn't have a clear semantics. It's not reversible. So, for example, if I write something like this, pxy, x is y plus 2, y times 2, and I'm asking for if I put x equal to 6, what is the value of y? Well, it doesn't know how to do it because it doesn't know how to reverse, how to flip things. So it's really completely unsatisfactory. The fact that you have to essentially give a value to the variables before you can do anything interesting forces, when you write Prolog programs, and to an extent even when you write answer set programs, you're forced to actually use a special style of program, which is what we typically refer to as generate and test. You first throw values at the variables and then you see if the values are good or not. Which of course is not very good because you first of all create a humongous possible search space and then you start pruning it. That's really not what you're supposed to be doing. And that's where constraint logic programming started coming around. Constraint logic programming is actually a fairly old paradigm. It was introduced in the mid-80s. It was a big result of the old 5th generation project that was around in those years. So the idea of constraint logic programming is to essentially say, well, I don't want this extra logical stuff that doesn't make any sense. What happens if instead I stick into my syntax something that has a well-defined meaning, a predefined meaning, so that I can actually get a result that makes sense. And I also want to be able to actually not do generate and test, but I really want to test and generate. So I first set up all the conditions that have to be satisfied, and then I start doing my generation so that if things go wrong, I immediately prune without kind of generating all the possible alternatives. So let me just give you the hello world of constraint logic programming, which is a typical puzzle, the sum plus more equal to money. So what we want to do, we want to associate to every letter here one digit, so that actually this sum is correct. And all the digits have to be different from each other. So if I was encoding these in Prolog, I would be writing something like this. It's fairly declarative. It does make sense. So what I have the variables that represent the different letters of the puzzle. I assign numbers to that using the members predicate. It's a built-in of Prolog that picks one value from a certain list. Of course, I need to make sure that I assign all different values because I don't want to have any repetitions. And then I just, at the end, check whether, indeed, sum plus more equal to money. It is declarative, it's readable. I can understand what's going on here. Of course, I have a humongous number of backtrackings because I first generate all the blind assignments and then I just backtrack. I can make these more efficient by simply sticking the different tests in the middle of the assignment. So essentially, I do the sum from right to left, just as you are taught to do. But now this is not declarative anymore. Not only, but also this gives us another issue of Prolog, which fact that it has a fixed order of evaluation. And here I'm taking advantage of that fixed order of evaluation, which makes things even less declarative. On the other hand, if I was writing the same thing in CLP, that's what I would be writing. Now, this is declarative. Not only, but it's efficient as well. So I declare my variables. I set a collection of constraints. I say that the variables must be in this range. I'm not assigning them, by the way. This is just a condition. I set the condition send plus more equal to money. The S and the M, which are the first letters, should be not 0. Otherwise, it doesn't make any sense. I have a built-in constraint that ensures that all the variables are distinct from each other. And this is my generation. So labeling is a built-in of constraint logic programming that just start assigning values. But I'm assigning values only at the end, after I've set up all my conditions. So constraint logic programming is essentially the marriage between constraint solving, CSP type of things, and logic programming in the style of Prolog. And that's where CLP comes into play. Now, CLP is actually a framework, which means that actually I can plug in different theories that gives different meanings to different pieces of syntax. So for this reason, very often, people like to talk about CLP-X, where X is the theory that I intend to throw into my framework. So the important thing to remember is that every component of the syntax that comes from X has a predefined meaning. So for example, if I have this particular component predicate that is part of the X, then I'm not going to find a rule in my program that is going to define the meaning of that. That meaning is going to be built into the system itself. It comes from the theory X. Of course, also the execution model is going to be different. When you actually run Prolog, what you do, you start accumulating assignments of values to variables. And that happens through unification. So you do perform unification and you keep assigning values to variables. When you do CLP, instead what you do, you keep accumulating constraints, which means you keep accumulating conditions. And what is very important is that you need to make sure that you can guarantee that that collection of constraints that you're accumulating are always consistent. That is, they have at least one solution. Okay? So, just I'm repeating a little bit myself. So we have this X. X gives a certain piece of syntax that is part of the language with a predefined meaning. That meaning is going to be interpreted on a predefined domain, for example, integers, and then the symbols are addition operations. And so while in Prolog this was just a unification between some symbols, now in CLP this becomes an equation that has to be solved. That's a condition between X, Y, and 3. So for example, this is a simple example that actually use the CLP instantiated on real numbers. So that's what we typically call CLPR. So we have a constraint that says that X must be equal to Y times 3. That's a constraint. In this case, it's identified by the fact that it's enclosed between these braces. Then I call QXY. This introduces another constraint which says X minus 2 equal to Y. So essentially I have a system of equations with two equations. And if I give a query PXY, I actually get a solution that says X equal to 3, Y equal to 1. Now, of course, we can do things that are fairly interesting. Like, for example, here I'm saying that Y must actually satisfy this condition with X, which means essentially I'm identifying this part of the two-dimensional space. Then I have another one. And the constraint solver should be smart enough to recognize that there is no intersection between these three areas. So when I give the query prog XY, I get no as an answer, which is there is no solution. So it's actually pretty smart. Let's actually be a little bit more formal. So when we talk about CLP-X, X is a constraint theory. In our case, the constraint theory is, first of all, composed by a signature, which means a set of symbols. We have a certain number of function symbols and constants, as well as a certain number of predicates. These are all the things that already have a predefined meaning attached to them. We have an interpretation structure, which assigns this predefined meaning to these pieces of syntax. And then we typically also restrict what are the legal formula that we are allowed to accept from all the possible formula that can build using this particular piece of syntax. For example, I may accept only conjunctions of things. I may not want to have disjunction because maybe my solver doesn't know how to handle them. Atomic formula built in this language is what we typically call the primitive constraint. So for example, something like X less than Y. That would be a typical example of a primitive constraint. X less than Y and Y equal 2 times 3, 2 times Z could be instead a propositional combination, which may be a legal formula in our language. So just as a simple example, I can have, for example, the set of function symbols are plus and minus, the predicates is equal, not equal, less than, and then, for example, I throw in this extra predicate that allows me to assign a domain to my variables, which means any number between n and m is going to be a legal value for my variable. In this case, the predefined domain is going to be the set of the integer numbers. The primitive constraints are any atom that I can build with these predicates. And then, for example, my legal constraints are conjunctions of primitive constraints, and I'm requiring that every variable shows up in one of these membership constraints. So just a simple example. So various X have been explored in the literature. So the most popular one is FT, which stands for finite domains, which essentially is CSP transported into CLP. There is CLPR, which is real number with linear constraints, CLPQ, which is rational numbers with linear constraint. There is a very nice piece of work on CLP over finite, hereditary finite set, which means sets that are finite or nested sets that are all finite. Prolog 2 is actually another CLP framework, which actually has constraints over finite trees. So now remember, these are the domains. Now these domains are embedded into logic programming. So we do have still the whole framework of logic programming, which means I can still write my rules. Okay. So the only catch is now these rules can have in their body either regular logic programming atoms or constraints that are drawn from the X theory that I've selected. And when I want to execute my programs, I give a goal. And what I'm essentially trying to do is to see whether the conjunction of these atoms are actual logical consequences of my theory, where my theory includes X as well. So for example, very simple example of finite domain constraints, little problem. In a farmyard there are chicken and rabbits. We know there are 18 heads and 58 feet. How many chickens and rabbits are there? So we have two variables, the count of the chicken, the count of the rabbits. I declare that these variables must be in the range 158. That's kind of stupid. I should have said 1 to 18. But what I want to know that the sum of the heads must be 18, so x plus y equal to 18. This is a constraint. That's the pound. The pound equal is the equality in the CLPFT framework. And then 2 times x plus 4 times y must be equal to 58. So very, very simple example. Now, there is a very large body of literature that shows how to give a semantics to the CLPX frameworks. There is a model theoretic semantics that is actually fairly complicated, so I'm not going to even talk about that. On the other hand, it's much easier to think about it in terms of operational semantics. So what happens when I actually give a query to a CLPX program? So essentially, the notion of state, the semantics is based on transitions between states. And the state is composed of two components. One is the goal that I'm trying to answer, and C is the collection of constraints that I'm progressively accumulating as I go ahead with my execution. This state is going to be successful if I run out of goals, which means I've determined that all the goals have been satisfied. And of course, the constraints that I've accumulated must be consistent. On the other hand, if at any point in time the constraints that I'm accumulating become inconsistent, then of course I'm failing, because it means that there is no solution. We assume that given a goal, there is actually a function that allows me to select what is the next element that I want to resolve. Let's call it alpha, selection function. And then we define one derivation step, which goes from one state to the next state. And of course, there are two possibilities here. So if the element that I'm selecting is a standard logic programming atom, which means not part of X, then I'm just going to use the traditional resolution. So I'm going to look for a rule in my program where the head looks like the element that I've selected. I'm going to remove that element from the goal, and I'm going to replace it with the body of the rule, as well as with a collection of equalities that make sure that the head of the rule can be made equal to the element of result. Now, remember, these are not unification as in Prolog anymore. These are equations, because these may have to be addressed by X. Okay, because it may include, for example, arithmetic and things like this. On the other hand, if the element that I'm selecting is actually a constraint, then the only thing that I have to do is to remove it from the goal and add it to my collection of constraints and just make sure that actually it's still consistent. Because if it is inconsistent, then I'm going to just fail. And then I can just build a sequence of steps of derivation, start with something that has everything in the goals and no constraints at all, and then hopefully I'm going to get to a successful final state. Let's actually look at the CLP-FD framework. So let's actually look at a specific example where X is a fixed interpretation. So in this case, the sequence of symbols that I can use are the traditional arithmetic operations. The predicates are what you would expect, equality, not equal, less than, greater than, plus these particular symbol that allows me to assign a domain to every variable. So every variable that has between n and m, where n and m are two numbers. This actually is a specific syntax that is used in one particular system, which is SWI Prolog. So for example, this particular predicate is actually encoded with a predicate in that particular syntax. And I can actually have constraints that are primitive like this, x plus 1 equal to y, over x minus 2 not equal to y plus 1. I can actually do conjunctions and disjunctions of constraints. So I can build fairly complicated formula. One of the interesting things that many CLP-FD systems, they have also introduced what they call global constraints, which are constraints that include many variables. And these are constraints that are, for example, all different, which ensures that the values that are given to these variables, that they are all distinct from each other. So it's a conjunction of not equal constraints, which are assembled and dealt with efficiently. Or, for example, another example is this that says the sum of all these variables must be greater than 10. And once again, this may include an arbitrary large number of variables. During resolution, of course, we have a constraint solver that is going to keep checking consistency of the constraint that I'm accumulating. Not only, but it's also going to try to simplify these constraints whenever possible. So, for example, if I have a goal that says x must be as a domain which is from 1 to 10, and I want x to be greater than 8, then this actor is going to be able to simplify this constraint to this constraint. Now, of course, remember the constraints, when I set them up, they're going to just set a bunch of conditions. So that's just the test part. I may want to actually be able to also do the generate part, which means force the assignment of values to these variables. So once again, the CLP-FD frameworks typically provide you with some search predicates built in that allows to generate these assignments of values to the variables. They typically have two arguments. One is the collection of variables that I want to assign, and then we have some options that allows to control in which order these variables are assigned. So these are some examples. I have variable selection strategy. So if I have a bunch of variables, which one do I assign first? So I can actually do a first fail, which means the variable that have the smallest domain, or first of all, or FFC, which is the variable with the smallest domain plus the variables that have the highest number of constraints on them, or maybe just the leftmost. Take the first variable that appear in this list and assign that one first. I can also decide which value from the domain of that variable to use first. I can actually either split the domain, for example here, I can actually take the middle point and really branch out into different directions, or just enumerate one value at a time, or for example, simply replace that variable with one assignment plus a not equal constraints for the other branch. So remember, this is the place where backtracking is eventually going to occur. I try one option. If I fail, I'm going to backtrack and try a different option. It is also possible to actually do optimization. So as an option here, I can say, well, not only assign the value to these variables, but you also want to maximize the value of a certain arithmetic expression, or minimize if I want to do that. And now let's actually move at the next step, which is the intersection between answer set programming and constraints.
Okay, so first we're going to dive a bit deeper into the constraint satisfaction side of things, and then we're going to get back to ASP and we're going to combine them. So as Enrico was talking about constraints, so let's look at the details of the definition. So when we consider a set of constraints and we want to solve them, we're essentially talking about a constraint satisfaction problem. A constraint satisfaction problem can be defined formally as a triple consisting of a set of variables, a set of domains, that is, domains for one domain for each variable, and a set of constraints. So a constraint itself is a pair consisting of a list of variables and a subset of the Cartesian product of the domains of those variables. So essentially we're saying which parts of that of the whole Cartesian product of the ranges of the domains, we're interested in, which subpart satisfies the constraint. So typically, rather than using an extensional definition, we like to use an intentional definition of our constraints, and so we'll write things like these, which you have seen before, right? So x less than y, but from a technical perspective, if you have a domain for x and a domain for y, x less than y is projected on a subset of the Cartesian product of the ranges of the two variables. So there's another kind of constraints which we consider in constraint satisfaction, which we call global constraints. Global constraints are they capture relations between a non-fixed number of variables, and we'll look at a few later. The simple one that we can focus on for now is the sum global constraint. So we're saying the sum of whatever number of variables listed here must be less than, say less than, just for sake of example, some value w. So here the number of variables is not fixed. So the next thing is to put these concepts in practice and see how we can play with constraint satisfaction. So consider that we have 3 integers. They can range between 1 and 10, so that's the domain of each of the integers. We want the sum of those integers to be 23, and so the goal is to find values for those integers. On top of that, we have an additional constraint that we should consider only odd integers. Okay? So how do we formalize something like that as a CSP? So remember, CSP is a triple, so the first element of the triple is going to be the list of variables that we consider. We have 3 variables clearly, right? 3 integers that we need to pick. So say x, y, and z. We said the ranges are between 1 and 10. So the variables range between 1 and 10, so the domains of those variables are going to be 1 through 10 for each of them. And then the key thing are the constraints, right? So how do we specify all that we have listed here? So the sum of them needs to be 23. Well, we can use a global constraint for that, right? We can just say the sum of x, y, and z must be equal to 23. How do we say that the integers need to be odd? Well, we can use the modulus operator and require that each of the operations gives 1 as a result. So this defines the constraint satisfaction problem corresponding to the specification that you see up here. But how do we solve it? Well, to see how we can solve it, first we have to worry about the semantics. So the semantics of a CSP, constraint satisfaction problem, is given by the notion of an assignment. So an assignment is a pair, x sub I, a, where x sub I is one of the variables from the CSP, and a is one element from the domain of that variable. Intuitively, an assignment says variable x sub I must have value a. That's the value that we have determined. We have a couple of extensions of the notion of assignment. So this assignment up here is only for one variable. As you can imagine, the moment we consider multiple variables, we have sets of these pairs. A compound assignment is one such set. Okay? And we talk about a complete assignment whenever all of the variables from a CSP, from the list of variables of the CSP, occurs in the compound assignment. So each variable needs to be assigned some value by the compound assignment. So a solution to a CSP is then a complete assignment that satisfies every constraint from the CSP. And an assignment satisfies a constraint, a pair like this one, whenever the values of the variables from the first element of the pair, if you consider the values of those variables from a given assignment, if those variables satisfy or fall within that subset of the Cartesian product of the domains of the variables specified in the second element, then the constraint is satisfied. And so a solution to a CSP is a complete assignment that satisfies every constraint. So going back to our toy example, it's easy to see that the assignment that assigns value 0 to x does not satisfy the constraint that x must be odd, clearly. At the same time, assigning 1 to x satisfies that constraint. And if you pick, for example, 9 for x, 9 for y, and 5 for z, that's a solution to the whole CSP. It's not difficult to see that these satisfy all of the constraints on oddity of the numbers, and they also assign, if I did my calculations right, the constraint on the sum of them. Right? So that's a solution to the CSP. Now, it's great. CSP is really convenient for dealing with these kind of numerical problems. Sometimes, however, we deal with problems that are more qualitative in nature, and so CSP is not as convenient. So that brings us back to ASP. So at some point a few years ago, not a lot of time ago, but a few years ago, people working in the ASP community started thinking, well, ASP is great, we can solve qualitative problems, but we can't really solve quantitative problems. Constraint satisfaction and the likes, such as CLP, help us solve numerical problems pretty well, but we lack that qualitative aspect. And so people started looking into ways of combining ASP and CSP. Constraint ASP, or CASP, up here, provides such a way of combining these two formalisms and sort of bring the best of both worlds together, the qualitative specification and the quantitative specification. A CASP can be viewed or you can view it as strongly related to CLP, which Enrico described earlier. In a sense, in both CASP and CLP, we have constraint satisfaction as the embedded language, so we can inject in there constraints that we're interested in, and then there is a host language around the constraints that allows us to sort of bridge things together and specify other parts of the problem. Now in Prolog, we have in CLP, we have two somewhat different constraint knowledge representation paradigms coexisting. The Prolog paradigm and the constraint satisfaction paradigm. The constraint satisfaction paradigm, heavily declarative. The Prolog paradigm, more or less declarative, depending on who you talk to and their point of view. In CASP, one big reason for the interest that people had is that both ASP and CSP have very similar knowledge representation paradigms, both highly declarative, both essentially based on constraints, just different types of constraints. And so that's the reason for people's interest in combining them. So let's look at an example of, a very, very first example of a specification of a constraint satisfaction problem using ASP, or something that looks like ASP. We'll get a little more formal later. So suppose I'm given variables x, y, and z with some ranges specified, and for now we're going to keep this at the informal level of the specification. Later we'll make it formal. I could easily have four ASP rules, in fact 4 facts, each of them written as equalities, assuming that equality is a legal symbol of the language, and I can essentially rewrite what we wrote earlier. So because these are facts, assuming that these are legal ASP statements, then we can find an answer set for them, right? And the answer set is straightforward. These are facts, so each of them is going to be in the answer set, and really nothing else is going to be in the answer set because we just have facts. So if I have an answer set like this, Well, I could view this as a specification of the constraints of a CSP. Not really the variables, we're not worrying about that yet, but at least the constraint part. So if I take this and translate it somehow into the actual constraints of a CSP, just with a syntactic transformation, then I can use a CSP solver, CLPFD, the solver in CLPFD, for example, to solve these constraints. So that's the high-level idea. But in what I just showed you, there's really no ASP except for the fact that those are facts. So it's just a CSP. So where's the ASP component of this? Well, we can elaborate the example a bit more. It remains a silly example, but at least it gives the idea a little bit. So suppose that I want to consider two versions of the previous problem. I want to consider a hard version and an easy version, or not hard version. So in the hard version corresponds to what we covered earlier. So the three numbers must be odd, and their sum must be 23. In the easier version, only the first of the numbers needs to be odd, the other two don't have to be odd, and then the sum still needs to be 23. Well, now I have a sort of a coexistence of qualitative and quantitative components. The qualitative component is the component that says, well, we want to consider both the hard and not hard versions of the problem, and we want to be able to solve both. And then the part at the bottom here is the quantitative part, where we state some constraints, and some of these constraints depend on whether we're considering the hard part, the hard problem or not. So this is a slightly more interesting kind of ASP program, because we have this junction here. Still facts, but at least we have some disjunction. And it's not hard to see that this program has two answer sets. In one answer set, hard is going to be stated. It's part of the answer set. So we are considering the hard version of the problem. And because of that, all of the heads of the rules that you see here are part of the answer set. So we're essentially requiring every integer to be odd. The other answer set corresponds to the easy version of the problem. So one component of the answer set says that we're solving the easy version of the problem, and then the other two elements of the answer set state the constraint on the sum, and then just the constraint on the oddity of x, nothing else. Okay, so we have two different answer sets, two views of the world in a sense, very ASP style. Now, because these parts on the right of the answer sets encode constraints, we can view them as constraint satisfaction problems, and we can solve them, right? So each of these answer sets can be translated into a CSP. We can find solutions to those CSPs, and a solution to the whole thing is given once we find one solution, so one complete assignment of one of these two constraint satisfaction problems. And if we want to enumerate all of the solutions, then we're going to find all of the solutions to each of these two constraint satisfaction problems, and those are going to give us the solutions, both the answer set and the numerical part. So a little more specific still. From the perspective of the syntax. And by the way, here I'm going to cover one of the variants of CASP. We don't really have a standard yet. We're getting close to a convergence, but no standard. But essentially all you're going to see here is easily transferable to the other flavors of CASP. So the syntax of CASP is the syntax of ASP. We just add a bit of syntactic sugar to allow for numerical comparisons that are usually not legal statements in ASP. But we have three relations that are pre-interpreted. They're fixed. Essentially, you can view them as keywords. The domain relation tells us that the argument D is the domain of the CSP. So Enrico earlier was talking about FD, finite domains, are reals. In CASP, we're going to talk about domain FD, domain NLP, NLP for nonlinear programming, nonlinear constraints, and FD for finite domains. And then how do we, remember I said earlier that the list of variables was given just informally. So how do we give it formally? We have relation var. The argument of var is the name of a variable that we're declaring to be a numerical variable. And this variable, and that's where sometimes confusion arises, this is a CSP variable. It's not an ASP variable. In fact, it's not interpreted as an ASP variable. It's just a string. And we have a variant of that statement where we can specify the lower bound and upper bound of the range of that variable. Okay? So that allows us to specify not only the list of variables, but also the second component of the CSP, the domains. And finally, how do we specify constraints? Well, we have a relation required. The argument gamma is the constraint that we want to assert. So essentially, this says constraint gamma is required to be part of the CSP that we're defining. It is in fact possible to use this kind of specification to go even beyond constraint ASP and do even more interesting things, but that's definitely out of the scope of this tutorial. So we'll stick with CASP and constraint satisfaction. So just quickly, our first example of a complete CASP program. So suppose that I have a set of resources, just 3 resources, 1, 2, 3. Some of them may be available, some of them may not be available. Suppose that we have knowledge of which ones are not available. So we will state it in terms of negation of available of resource 2, for example, that says 2 is not available. And then every resource that's not explicitly stated as not available will be assumed to be available up here. I is available if I is a resource, and I have no reason to believe that I is not available. This is highly ASP style of representing knowledge. This exploits non-monotonicity of ASP. So if I add a new resource in here and I say, hey, this is not available, immediately my reasoning system will be able to absorb the fact that it's not available. But if I don't state that it's not available, it will assume that it's available. Okay, very non-monotonic behavior. The numerical part of the problem here is defined at the bottom. So what we want to say is that every variable must be between 0 and 5. Very easy. There's actually multiple ways of doing it. This is a bit of a overly complicated thing, but just to show you all of the ingredients of the syntax. So let's say that the values of our variables must be integers. Okay, so we're going to state that our domain is FD, finite domains. And here we declare our variables. Notice what we're doing. We're saying, well, we don't care about the variables for the resources that are not available. We don't care about the resources that are not available. For the resources that are available, we're going to have, say, a start time for that resource, represented by variable x of I, where I is the resource itself. And then to state that the value of the variables must be between 0 and 5, we can write 2 additional rules. Each of them will say if the resource is available, then its start time must be greater than 0 or less than 5. Okay. To go from this to a constraint satisfaction problem, as we discussed already, the first thing we do is we find an answer set of this. That's doable. You just use the definitions that Song gave earlier. How do we get to an actual CSP? We need a translation from the answer set to a CSP. Now, the translation, if you look at it at the high level, from a high level perspective, is pretty straightforward. Essentially, you just need some bijective function that will take any CSP constraint and we'll map it into a legal ASP term. For example, x greater than 2.4 could be mapped into GT X, comma, and 2.4 in double quotes because ASP doesn't really, typical ASP flavors don't like floating point numbers, and they want to look at them as strings. As long as you define it in a bijective way, we're okay. In fact, what we're interested in is mostly the inverse of this function that allows us to go from any arbitrary ASP literal into the CSP constraint that literal represents if it's a literal of the form required gamma. So essentially we just take gamma, remove all the syntactic sugar, and we get the constraint. Or just a vacuously true constraint for any other literal, so that we can apply this inverse of the function to a whole answer set. And that's going to extract, if you think about it, it's just going to look at all of the required statements and it's going to extract the constraints. Those are the constraints in our CSP. Example at the bottom here of the inverse function of the translation applied to GTX 2.4. That's, as you would expect, it's going to give you x greater than 2.4. So the answer sets of a CASP program. So here we're looking specifically at a flavor of CASP called Easy CSP. It's a simpler language than others, convenient for what we're going to show later. So if I have some program pi, first of all, remember that's an ASP program, so we can also talk about answer sets in the sense that Son defined earlier. So we're going to talk about answer sets of A under the ASP semantics if we apply the definitions that Son gave. We are also going to denote V of A, where A is an answer set of, under the ASP semantics of pi, as the set of variables declared by that answer set, and the variables declared by the answer sets are just correspond to the statements of the form var of x. Now, an answer set of pi under the easy CSP semantics, or an easy CSP solution, is now a pair. The first element of the pair is the answer set of pi under the ASP semantics. So you look at the program, get an answer set. That's the first element of the easy CSP solution. The second element is obtained like this. Take that answer set, A, apply the translation function, in fact the inverse of it, to extract the CSP. Solve the CSP, find one solution, that's your N. Okay? So that pair summarizes the answer set and one solution to the constraint satisfaction problem defined by A. And so that brings us back to, we started from constraint satisfaction, that brings us back to full-fledged ASP integrated with CSP. And so once you apply the definition of answer set of easy CSP program to the small program that we considered earlier, it's not hard to see that the answer set of the program under the ASP semantics is what you see here. Now, the answer set under the easy CSP semantics will be obtained by looking at the solutions of the constraints encoded by A. So A encodes the constraints shown here. x1 must be greater than, and this is a typo, it should be 0. x1 is greater than 0, x1 is less than 5, x3 is greater than 0, x3 is less than 5. Nothing about x2 because x2 doesn't exist at all in our CSP specification. We find the solution of that CSP, say x1 equals 1 and x2 equals 2. There are other possible solutions that you see here. So for each of them, we have a separate answer set under the easy CSP semantics, where the first element is the original answer set under the ASP semantics, and then the second element is one of those solutions. Let me skip this part. Okay, so so that's the theory, right? How do we use CASP in practice? There's actually a number of CASP solvers by now. What we're going to use later in this tutorial is Easy CSP, same name as the language. This is a research tool. It's not to be viewed as a production system, although it is reasonably robust and reasonably fast, but it's not intended as robust as a production system. It's intended as a research tool. You can take it, plug and play things in it, see how they work, experiment, understand how new combinations of solvers, for example, or solving technologies work. So the diagram is shown here. I'm definitely not going to go into the details, but the idea is this system takes an input, some problem specified either directly in EasyCSP or in some other language. For example, PDDL+, we have a way to take a PDDL+ specification and turn it into an EasyCSP program. From the EasyCSP program, you apply the core solver here, which finds an answer set of the EasyCSP program under the ASP semantics, then translates into a CSP and finds a solution to that CSP, feeds the result back here. Now a whole EasyCSP solution has been found. That solution is piped out of the system into this component that you see up here, where we do additional checks on an application depending on the application that we're trying to solve. For example, in the case of PDDL+, we have a translation that translates PDDL+ into EasyCSP in such a way that invariants are not necessarily guaranteed to hold within the duration of a state. So this component up here then uses an external validator of the PDDL+ specification to check if the invariants are satisfied. If they're not, then we look back in and we look for another EasyCSP solution. And so the reason why I say that this is a research tool is because it's designed so that we can plug in our essential arbitrary ASP solvers and constraint solvers. So in fact, the interesting part is really the constraint solvers. We have played with different CLP systems that we use as constraint solvers. We have played with pure CSP solvers such as G-code, or really EasyCSP supports any Minizinc solver. We have also played with algebraic modeling systems, and they all fall easily under this big umbrella. And with this, I'm going to move on to Son.
So far, we gone through the basic on all the flavor of logic programming, and I wanted to say that depending on your application, one may be better than the other, and I think that through the course of the tutorial, we will see some example of that. And by the way, if you have questions, please go ahead and ask questions. So now I will introduce very quickly a little bit the action description language that we are going to use to formalize the planning problem and all the related application. So the motivation of developing action language is like we want to have a language that is declarative, that is elaboration tolerance, and also it allows us to develop efficient and scalable reasoning algorithm. So we will take the action language description, the action language B that was first proposed by Calfon and Lipschitz, and so basically the action language has two components. One is so we define the element of the domain that consists of fluent and actions, and then what we will formulate a planning problem as like a domain D with the initial state I and then the goal O, right? So that the basic elements of this action language have the three components. One is to define when an action is executable. It is written like this. It can be different. So an action language A is executable if there is a list of preconditions, if the set of preconditions is true. And then the dynamic causal law that says that under the condition that this list of precondition is true, then execution action A will cause that fluent literal become true, and static causal law that is the list of preconditions will cause something to be true. So I will just, and then the initial state would be described by the predicate initially and the goal. And I will just give you a few examples of how this is used. And so here, for example, this is the encoding of the yell shooting problem. An extended version of that, like initially the turkey is walking and it's not dead, we can write something like that. The gun is loaded like this, and we have like okay, I reverse a little bit. I reverse. So here action should cause a dead if the gun is loaded and the gun to be not loaded. So and so here I think that I reverse. So here, if the turkey is dead, then dead turkey cannot walk. So that, and now we can have this. So basically, we can write something like this is the initial state, and that is the set of laws that describe is the domain. So I will keep a little bit of like B and PDDL is very closely related. So basically, we can represent most of the element of B in PDDL. So there's mostly the one-to-one corresponding like conditional effects, executable conditions, and the only thing that is not is a static causal law. I'll talk a little bit more about that. So here it basically in PDDL we have so we have these axioms, but and this is they either call it defined fluent or axiom, but it is required that they are not acyclic. They have to be acyclic, basically. Whereas in action language B, you can have cyclic static causal law, and that's a very. And I wanted to mention that if we can deal directly with static causal law, the efficiency, so planning system would be better off, and that's study in. Oh, I forgot to recompile. So it is there is a paper by Silver talking about Silver and who's that and some other people saying that it is better if we do have work with that. The main thing is that not many planners deal with this, and there is one thing that is if the static causal law are acyclic, then it's easy to deal with it. But the static causal law cyclic, it's not that easy, and that's the problem with that. So I'll give you a very quick semantic of that, and then I think that so intuitively, action theory defines a transition between set of states, between state and state. And so it designs a transition system where we have a triple here, state, action, and state. As an example, here we have like if the turkey is walking, it's not dead, and the gun is loaded, shooting will create it to the new state like that. So basically, and I will not go over the formal definition of the transition function, but that here I just wanted to mention here. This is how static causal law is dealt with in action language. Basically, we define a closure of a set of literals so it's a smaller set of literals that contain this and satisfy all the static causal law. And what does it mean to be satisfaction? It means that whenever the list of precondition of that static law is satisfied, then the consequence must be in there. So that is in that. And so the transition function is defined. It basically because with static causal law, the transition function could be non-deterministic. And so from one state you might go to different, and the reason is this equation. So the idea is that when you execute an action, all the direct effects of that action have to be satisfied. But then all the indirect effects of that action should also be satisfied. But depending on the static causal law, there may be different different way of creating the indirect effect of action, and that's where that is. So that, and here I will just briefly go over this. It's like a few examples that I will mention later on in the tutorial. So here we probably all of you familiar with the bomb in the toilet domain, right? So here we have this simple example where we have only one package, and this is basically the transition system of this thing. So we have the action done causes disarm the bomb. If it was disarm, and so we have essentially these 4 states, and that's the transition like that. In this example, we don't have the non-determinicity. Yeah. Another one is so this is an example where statistical law is really helpful. So we have a bunch of domino like that, and then if you touch one of these, so all of that to the left will fall down, for example, and that's the. So if we have 1,000 of them, one action would be able to, we would be able to make the last one here to be falling down. But if statistical law here is treated in the way statistical law is treated in traditional planning system, like converted it, combine it into introducing actions. And in that case, thing is bad because you will create a number of like 1,000 of action and so on and so forth. So, and then here again, that's where the statistical law, we have another example where basically we want to have, when we have the burner to turn on. So the statistical law of that, like if this is open, then gas will run from here to here and so on and so forth. But so that the final answer of this one is that we have to be open, but open one at a time in this order. And that's also one of the examples that we used to show that treating, dealing directly with statistical law is really important in application. So now we have, I think 3:30 is so I think that I can cover the first part of this. How do we use logic programming to do planning in 2 aspects? So first, I will talk about using answer set programming, logic programming, and CLP in classical planning. So to get the idea, the basic idea was that to solve a problem, we translate it into a logic program so that the solution is corresponding. So what we can do is that, I think that we did a better job with that. So we need to, in classical planning, I wanted to mention that basically the reason we could use answer set programming to solve it, that if we restrict the bound of the plan, then we could solve the problem in here, like in NP complete, and the complexity of computing an answer set is also NP complete, and so that's the reason we do that. And we can do that in the sigma 2p cases when we have that. So in the early days of answer set planning, there are approaches. So the idea is that basically when we have a planning problem like that, we will create the rule like this. First, to declare the fluent and the action. They are used as a constant of the program. And then we define the initial state. We define when the action is executable. And then we added one more rule that is the choice rule to generate the action occurrence. And then we would develop rules that compute the effect of the actions and solving the frame problem, the ramification problem, and then add the constraint for checking the goal condition. So here it's here the detail. So first we will restrict. So we will we define the constant from time from 0 to n to say that we are interested in plan of length from at most n. And we define for each of the fluent, we have this fluent, we have the action, and then we define this literal f just to say that like we are dealing with F and not F also. And then for each of the executability condition, we define possible A at the time t if this condition is satisfied. So that's very standard way of writing program. And then for this static causal law, we write, so this one is true if this one are true. Also very standard. And then for each of these dynamic causal law, A causes L, if this we write, if A occurs at the time t and the precondition for that effect to be true is true at time t, then its effect is to be calculated at t plus 1. So, and then the state consistency, we don't want to have, we define F and not F, so therefore we don't want that to have this thing. The state have to be consistent anytime. And then to solve the frame problem, we have this saying that if a literal L is true at the time t, and its complement is not true at the time t plus 1, then it must be true. It must continue to be true. To define the state, we say if we have L is initially true, then this is it's true at the time 0. And then to force that the code to be true, to check for the constraint at the end, we just write if L is in the code, then it has to be true at the time n, what is the constant that we have. The generate the action, we use this choice rule here. At each of the time t, we have at most one and at least one action that have to occur. And we require that the action can only occur whenever it is executable, and that's all the programming. And we can have this. If we have no static causal law, this coding can be simplified quite a bit. And here is an example of this bomb in the toilet domain, where this is mainly that to define the fluent, define the actions, and define the executability of the action, and this to define this should be possible, but and then define the effect of the action. I omit the rule like say generate action, occurrence, the inertial rule, and so they are standard for all of the domains, so I did not include any here. So I think it may be a good time to stop here, because we will look at the encoding of the problem in CLP next. So I think that probably we stop here, and I hope you come back at 4.
But you are not stopping.
Huh? That break here is not stop here. So Enrico will continue after this. So we have the break.
Okay, let's actually restart. Maybe people will slowly come back in. So Son has made a great presentation showing how to map an action language like B into answer-set programming. Let's actually see another option, which is how do we map the same thing to constraint logic programming, just to see what are the differences and whether there are advantages or not. So the idea are actually fairly simple. So we are actually mapping action description to finite domain constraints. We create separate variables to represent fluents as well as to represent occurrences of actions. And we just map the entire action theory on a collection of constraints. And then the resolution of constraints should correspond one-to-one to actually the plans that actually solve the problem. Why do we do that? Well, some of this is kind of a repetition of things that we have already mentioned before, because they're really shared with ASP. So the fact that we have a declarative encoding gives us elaboration tolerance. So for example, if we have new pieces of knowledge that that become available, we can just add them. We don't really need to change the system. We hope that actually CLP is giving us propagation techniques that can actually, hopefully, lead us to converge to a solution faster. CLP is very good in providing sophisticated search techniques. And that's something that actually is an advantage over answer set programming. In answer set programming, once we have the model, we feed the model into the solver, we have no control on how the search develops. In CLP, we can write the search procedure, so we can decide how actually things are assigned in which order. Global constraint represent also a very elegant mechanism, for example, to introduce control knowledge about, for example, things that we want to see happening over all the plan. And as we're going to see towards the end of this little section of this presentation, the mapping of action languages to CLP also inspired extensions of action languages, where we take some of these constraints and we bring them up to the level of the action language themselves, which makes the description of planning problems even more declarative. So the idea actually of how to map a language like B to constraint is actually fairly simple. So we're looking at a sequence of states, just like the encoding that we had in the case of answer set programming. We assume that we have a finite horizon, so a finite number of steps. So what we do, we introduce for every fluent a new variable that represents the value of that fluent at that particular point in time. And of course, we're going to have to somehow connect the value of the fluent at time I with the value of the fluent at the time I plus 1. Similarly, we introduce variables that represent occurrences of actions in the transitions between one state and the next state. So for every fluent f, we introduce a variable fi for the time I, which is the value of the fluent in that state. And similarly, for every action A, we introduce a variable AI. And of course, this variable is also going to be a Boolean variable that denotes whether that action is executed or not during that particular transition. This picture is a little bit more refined, so we have a collection of fluents. So we have the variable that corresponds to that fluent at time I, similar things, value of that fluent at time I plus 1. These variables are Boolean variables that denote occurrences of action. And if we want, for example, to have a sequential plan where we execute only one action at every time steps, of course, the sum of these variables should be equal to 1, because only one variable, only one action is performed at every time step. So, of course, if we want to determine the value of a certain fluent at time I plus 1, this fluent is going to be true only under two possible conditions. Either we execute an action in this transition that makes that particular fluent true, or we have that the fluent was already true in the previous time steps, and there is no action that is fired that makes it false. Okay, so inertia will allow us to preserve that particular value. So how do we map all these now to a collection of constraints? It's really mechanical, but intuitively it's not difficult. So first of all, let me introduce a little bit of notation. So given a formula, which means a formula that describes, for example, I don't know, executability conditions or the precondition of an action, we actually map that formula to phi I. And what we do, we take the formula and we replace every atom that is in the formula with the corresponding constraint variables at time I. So essentially we project the formula to time I. We also use these symbols alpha, beta, delta, gamma, and nu to represent the different conditions that appear in our action theory. So alpha are the preconditions of this particular action that makes F true. These are the preconditions of the same action that makes the fluent false. These are the static causal laws that makes F true. These are the static causal laws that make F false. And these are the executability conditions. So we can actually talk about all the different things. So the collection of constraints that we build are essentially used to capture this idea that I just mentioned. A fluent is going to be true at the next time step, either if it is true before and it's not made false, or we perform an action that makes it true. So first of all, we have general conditions. As I was mentioning, we assume that we execute only one action at a time, which means that the sum of all the variables that represent action occurrence at time I must be equal to 1. We can perform only one action at every time steps. Furthermore, we need to ensure that actually we execute only actions that are executable, which means that if a certain action J is executed at time I, then at least one of its executability condition must be true at time I. Once again, these are a collection of constraints. So it's a disjunction of constraint that we are asserting. Positive fluent, so we introduce a few intermediate variables just to make things more readable. It's not essential. So this post-fired I essentially is a new constraint variable that we introduce to denote the fact that we are actually performing at time I an action that makes the fluent F true. So it makes it positively true. When does that happen? Well, it happens either let me backtrack. So post Finite I means that we're actually making the fluent true. Okay. So when do we make the fluent true? Either if we perform an action that makes it true, or if there is a static causal laws that make it true. So either we are actually firing at time I an action that makes it true, or at time I plus 1, which means my destination, there is a static causal laws that makes that fluent true. So this actually is the condition for the static causal laws. So we make the static causal law for f true if one of these constraints, and these are, if you remember, these are the constraints for the static causal laws. Okay? So if there is one of the constraints that is true that makes at that particular time the fluent true, this one is instead the firing one action that makes the fluent true. So we make the fluent true because of an action if the action occur at time I and its preconditions are satisfied. Once again, disjunction of constraints. We have the same thing for the negative, because not only we have to reason about actions or static causal law that make things true, we also need to reason about action or static causal law that make things false. That's important for inertia. So it's the same, exactly the same thing, symmetrical. So the fluent f is going to become false at time I, either if we fire an action that makes it false at time I, or if there is a static causal law at time I plus 1 that is going to make f false. And that's essentially the same thing, except that here we're looking at the action that makes that false, or the static causal law that makes things false. And then we just basically put all the things together. Okay? So f is going to be true at time I plus 1, either if we make it true because of an action or a static causal laws, or this is inertia. It was true at time I, and there is nothing that makes it false at time I. Okay? So it's very similar to what we have in ASP, just written in different terminology, by using collection of constraints. And we just put together all these constraints. So these were the collection of constraints that talks about one fluent. Now we have to do it for all the possible fluents that we have in the language. And that's, again, only one transition. Then you have to take it for every single transition in your finite horizon. Okay? So it's possible to actually prove some theoretical results about this encoding. So first of all, we can actually show that this encoding correctly captures the transitions of the action theory. So if the action theory have a possible transition that goes from state I through the action A to state A plus 1, then if we actually look at the solutions of that constraint that we just built, we get that actually indeed this is a solution of the constraints. The reverse is not trivial though, in the sense that actually if we just look at things as they're being encoded right now, and we just take the constraint version, that can give us some solutions that we don't find in the action theory, which means solutions that are wrong. Why does that happen? Well, actually, in a sense, Son has already mentioned this when he was introducing the issue of static causal laws, when we talked about cyclic static causal laws. Those are actually not handled properly. And this actually is a very simple example. So assume that we have a very simple action theory where we have three fluents f, g, and h. We have only one action A. The action A makes f true. It doesn't really matter. We don't even use it. But then we have two static causal laws. One that says that if h is true, then g is true. And the other one is the opposite. If g is true, then h is true. So it's a cycle. F and G and H support themselves. So if you actually look at the action theory itself and you look at the semantics of a language like B, then you will see that actually starting from a state like this where everything is false, there is only one action that we can execute, which is the action A, and this is the only state that we can reach. So the action A makes F true, but then everything else has to stay false. There is no reason for changing the value of G or H. On the other hand, if you start looking at the encoding that we have just done using constraints, this actually is the collection of constraints that you get, and you end up actually showing that there are two solutions. One is the expected one, okay? So if you start from f at time 0 equals 0, which means it's false, g is false, h is false, and we perform the action, one of the solutions of the constraint is this one, which correctly map this, so f becomes true, and g and h remains false. But actually we find also this other solution, the one that f becomes true, and also suddenly g and h becomes true. Why? Because they support each other. And it's a solution of the constraint. There is nothing that prevents it. Which means that our constraint system does not know about minimality of changes. Okay, so it tends to change other things that don't necessarily need to be changed. Is it possible to fix that problem? Yes, it is. It's not trivial. I'm going to just give an intuition. We have a paper that describes all the details. The idea is to essentially really capture all the loops and make sure to kill the loops. How? By introducing additional constraints. So we essentially look at all the possible loops that we can create between the static causal laws, and we introduce constraints that says, well, if for any reason one of these loops comes into existence, kill it. Okay, so don't allow changes to that particular fluence that are involved in this loop. Okay, and under that conditions, now we can also prove the other results, which shows that the encoding is sound and complete. So we found all and only the solutions of the planning problem. So this essentially takes us to the idea of actually we can use constraint logic programming just as we can use ASP to compute solutions to planning problems. As I was mentioning, this also inspired us when we started looking at this, at proposing extensions of B. So we came up with this other language which is called BMV, where we actually took some of these things that we use in the encoding, and instead of keeping them hidden in encoding, we brought them up to the level of the action language itself. So we invented this language that is called B, where the fluence, instead of Boolean, there can be multi-values, because we map the fluence to constraint variables. There is no reason to limit to 0, 1. We can actually have a domain attached to that. So we can declare as variables that fluent that have a value between v1 and v2, or maybe even a set of possible values. When we actually map these constraints, we create the constraint that represent our problem, we actually have access to the entire history. So for example, we can also do reasoning that goes back in time. So I can have an action that says, if the fluent f was true 3 times steps before, then do something else. So we can actually have this kind of backward references. They are very trivial because you just refer to a different constraint variable you're encoding. And then you can also, of course, since you have multi-value fluence, you can actually talk about building arithmetic expressions with fluence and do comparisons between fluent values and so on and so forth, as you would expect. So you raise essentially your constraints to the level of the action theory. And now the laws that you have in your action theory becomes laws that have constraints instead of just atomic propositions as we had before. So the dynamic causal law says if the constraint C is true and you perform the action A, then you get to a state where the constraint C1 has to be true. So it doesn't have to be just make this fluent true, but you can have a complex constraint formula. Similarly for the static causal laws becomes implication between constraint. At every state, C1 should imply C. Okay. Similar for the executability condition. So it has several advantages. It allows compact representation on numerical domains. So we can talk about numbers, for example, in our action theory without having to do anything very complicated. If you try to do the same things in B, you would have to essentially create a long list of additional fluents for describing all the possible values that a fluent may have over time. Mapping these language, this extended language to constraints is essentially the same one that we had before, just a couple of differences. Now, of course, your fluent variables are mapped not just to Boolean variables, but variables that have a domain. Everything else is pretty much identical to what we encoded before. Still the same complication in dealing with cyclic static causal laws, but we know how to handle that. So we tried a little bit of experiments. We took a bunch of problems from different sources. Some of these come from planning competition. Some of these are ASP problems that we have encoded as planning problems. And the results are sort of mixed. So what we have here, what we did, we actually compare our encoding, we call this 6-plan because we use the 6-2 CLP solver, with the ASP implementation that Son described before. This simple picture tries to summarize the percentage of instances for the various problems that we are able to solve within a certain time limit. And there are some situations where the two are comparable in terms of number of solutions. There are some problems where actually the CLP implementation is better. There are some problems in which instead the ASP implementation is better. So it's kind of like there is no clear winner. If you look at timing, this actually that's kind of interesting. So in these we took some of the more complex instances that we have in the different problems. These actually are the different lengths of horizons that we allow in the planning problem. This is ASP, this is our constraint logic program. Ignore for a moment the last column. Don't look at it yet. So as you can see, there are two numbers for each one of these. Why? Because there are really two things that we try to do when we solve a problem using either ASP or CLP. When we use ASP, remember, Son mentioned we need to have a ground program, which means that grounding should be part of the problem. So the first component here is how much time it takes to do the grounding. And that time can be significant, because for some of these problems, the ground is huge. So for example, for this barrel problem, this is the 3-barrel problem, we have that actually we spend 185 seconds just doing the grounding, while instead the search for the solution took only 43 seconds. So really, search is fast, but to get there, you have to do quite a bit of work. In the case of the CLP, there are still 2 numbers. The first number is the time to set up the constraints, because we actually have to translate the B encoding into our problem and set up all the constraints. The second one is the search. So, for example, in this case, as you can see, the search, we lose against ASP. But on the other hand, it doesn't take any time to actually create the instance of the problem. This actually is an interesting problem, this community problem, because here we run out of memory. The grounding is just too huge for ASP to handle it. On the other hand, instead, CLP can actually handle it because we don't need to do the grounding, really. There are some problems where we actually can win in terms of both creating the constraint as well as searching. There are some problems where we are fairly comparable. There is no big difference. What I think is very interesting is actually looking at this one. This actually is instead, we took the same problem and we re-encoded it using our extended language, the one where we lift the constraints at the level of the action theory. And in this case, as you can see, the results are very interesting, which means that there is really a significant advantage in actually making the constraints part of the natural encoding of the problem. And this shows that actually we can even solve many more instances by using BMV with respect to either ASP or CLP. So there is an advantage here in constraint logic. It's not always true, but there are classes of problems for which clearly there is a big advantage. Son, I think you're next.
So I think that I wanted to add to what Enrico was just saying is that there are something similar like what Enrico was mentioning in the planning community, is that like the group of the planning group in Freiburg, they develop a language that allow numeric fluence instead of Boolean fluent. And then they did also do some they show that that language even in, I think that most of their in their planning system, what they did is that they convert the problem into a multi-value fluent before they try to solve it, and then it's a lot of speed up. Okay, so now I'm going to switch gear again to using logic programming to solve to address a few issue in planning, and in particular. What I wanted to show is that how easy it is to solve, to add that features to the planning system. And the first one is planning with preferences, and the second one is planning with domain knowledge. Okay. So why do we want to find planning with preferences? And I think that's a very huge, it's one of the research topics that is very interesting in planning. One of that is like, there are several problems that we like to have certain preference about our solution. Especially sometimes there are solutions that we would like to find first or would like to use. And that's in CLP, it's called soft constraint, but something that maybe we don't want, really don't want to impose on being the goal, but if it is achieved, we would be much more happier. And in planning, for example, in planning, I think there's an example, like say that, take an example of going to the airport. We have several choices. We can take a taxi, we can drive there, we can take the train, or we can even walk, right? So in planning, if we have the 4 actions, any of that could be considered as a plan. But we have preferences, our own preferences. So what plan? Depending on how far it is, maybe 5 minutes of walking, we would just take that one. Or if it is, we really wanted to don't want to do parking, then taxi is probably the choices. So how do we do that? How do we how we solve the planning problem with preferences? So of course we won't have the planning problem by itself, right? And then we will just, how do we solve that in using answer set programming? Very simple. You just need to add additional constraint to the problem. And how do we do that? We basically wanted to first represent the preferences that we have, and then add that constraint to the program that we already developed in the first part, and to enforce this constraint. So Enrico and I developed a language that called PP, standing for planning with preferences in planning, that have different complexity. So one is the basic design, the other one, the first one is basic design, second one is atomic preferences and general preferences. So preference formula will be evaluated with respect to a trajectory. So basically it evaluates, given we wanted to evaluate a formula with respect to a trajectory of so basically a plan. And we define a more preferred relationship between the trajectories, and then we develop logic programming rule to express this in the code, and we just call the solver to solve it. So we have two types of basic design. One is the state preferences, and the other one is the trajectory preferences. So we could say, for example, we wanted to express, I wanted to visit certain state before we reach the goal. That's the state preference, and it expressed by the form like either this action have to occur at some state, or this fluent formula have to be true, or this goal have to be true. So this is the additional thing that we wanted to have in the final course. And then we use temporal formula over the state preferences to construct basically the design for the whole, the preferences over the trajectory. So we use like the conventional like temporal operators like next, eventually, always, and until. That's the usual. So and then we define the preference relation over the basic design. So given a trajectory like this, and we have a formula phi. When does it say that it is? What does it mean for alpha to satisfy phi? So that if this is the case, we have to go over all this case, and that is exactly the same, almost the same as with temporal logic. Right? So that, for example, if we take like phi is next of this form, then we want to have phi to be satisfied at S2. That basically it. So with this, we can define what does it mean for a trajectory to be more preferred than the other trajectory. So if we're simply saying that if alpha satisfies phi and beta does not, then we say alpha is more preferred than beta. And we say that alpha is no better, no worse compared to beta if this case holds. So and then we can add additional structure to these preferences by defining the notion of atomic preferences. So atomic preferences, basically we have multiple temporal formula. So we would prefer one over the other. So this one. So this one is more preferred than this one, more preferred than this one, and we have the general preferences. So we will build formula, another level of comparison on this one. And I will not go over the semantics of this, but basically we define when does a trajectory satisfy. And now we have the language to express the preferences. Then we can basically, how do we implement it in answer set planning? We do exactly the same. We can just define the notion of what does it mean for a trajectory, for a formula to be satisfied. And so we could check that satisfaction, and then that we can do, which defines this satisfied phi t to say that the current trajectory satisfies this design. So you remember that when we generate the plan, we generate the action occurrence. So that basically gives us the trajectory. and then we just evaluate the formula with respect to the trajectory, and that is. So we will basically, I will not bother you with all this, but basically this is how it works. We will first we will encode the formula file in this way, and then we define the rule for certifying. When I say if a goal is like this and F is satisfied at the length, then the formula is satisfied. And basically that's how we can check for the satisfaction of a formula given a trajectory. Remember, we already have the trajectory and we just need to check for its satisfaction, and that's how we can do. And we will define. So basically, we have this program PI. So the action theory, initial state, the goal state, and then we have this formula file. We define the encoding of it, and then we have the program. Now we can do the similarly for the implementation of general preferences, but because of the general preference, we have multiple formula. We have to evaluate that. So we'll make use of the weight atoms of logic program to do that, and that's how we can do. We basically calculate the weight of a formula given a trajectory in this way, and show that if we can do that, then we can. So this is how we did it with the general preferences. Of course, the implementation of this one, it basically it's more like a prototype. It doesn't scale up very well for the reason is that, as Enrico mentioned, the grounding program, it's too much, and it does not work very well with it doesn't scale up very well. So the second part of this one I'm going to talk about is the planning with domain knowledge. The very similar idea we can use to exploit the domain knowledge in logic programming, like in I think that you probably there are at least 3 types of domain knowledge for a planning problem. One is temporal knowledge, the other one procedural knowledge, and hierarchical knowledge. They are all so there are a lot of paper written about this one. There are a lot of paper written about this one. This one is very this one, even though was discussed very early on by John McCarthy, but it's only used in the context of programming with robotics. I can see that they use that to in the Colloq project, for example. But not many system was able to exploit this type of domain knowledge. So the advantage of using domain knowledge in planning is, so one is like for efficiency, and the other one scalability. We did experiment with these ideas in ASP, and it gave us the same kind of like result here. The very similar idea to planning preferences can be used to do that. If we can also specify the formula, and we will say that okay, this temporal formula have to be satisfied, and we can define again this kind of like, when does this formula true it's satisfied given a trajectory. We do exactly the same, and then we just add the constraint that force the formula to be true in very much in the same way that we use with. So it's that. Okay. So now I'm switching a little bit. I'm again. So I show you how answer set programming deal with the incomplete information, conformant planning, and conditional planning. So the conformant planning and conditional planning, it's basically address the issue when we don't have incomplete information, and we have as well as sensing action. And the complexity of this problem are more these are harder problem comparing to the to the classical planning problem. And here just some example of that. To give you an idea of what I'm really talking about, so let's take up the example of the. Suppose that you are a contestant and on the TV show, and then they was the host asking you. So there is two doors like this. One of that is a tiger, and the other one is a goat. You open the right door, you get the goat, and otherwise you will meet the tiger. Okay. So what is your plan then? Your plan, and assuming that this is a real state of the world, but you don't exactly know which door it is, right? So that's something that you cannot just come up with a plan of say, oh, I'm just open the right door. That's not going to work, right? And that's the scary part is that if you open the wrong door, that the consequence will be bad. So a more reasonable plan is like, first of all, you have to determine where the tiger is. And it means that you have to enrich your knowledge by doing certain things. For example, you can make the noise so that, or you can do a kind of thing so that, or smell for the tiger, right? Or you make the noise and then listen whether the tiger does something, because we know that the goat cannot do anything. And then you open the other door. So, the roughly classification of planning with incomplete information, we can divide it into two things. One is conformant planning. So conformant planning, basically you find a sequence of action, and that guarantees that it will lead to the goal. Whereas, so each of the nodes in here that a set of states that represent possible state that you think that you are in. And conditional plan, so the initial state is complete, and you have sensing action, and action may be non-deterministic as well. So plan is often plan in conditional plan, as I classify that it basically is a policy, or at least a conditional plan with if then else construct that. So to quickly, so state of that, this problem have been addressed by many people, and so with sensing action in single agent environment. So, and just to quickly to give you an idea of the approach to reasoning with incomplete information. So there are two main approaches. One is like possible word semantic, and the other one is approximation. Possible word semantic is like it's basically we can extend the transition function that I have shown you in the previous part to cover the over belief state, and the other one is modifying the transition function to transition function over the set of approximate states. And here just to give an idea, so we have the belief state. I believe the state is just a set of state, and I will use S and sigma interchangeably. So sigma is the set, and S is just a set. This is a set of belief state. Whereas approximation state, we have just a set of fluent litera. So that approximately what we know for sure what is true in the world. And so I will keep over that. We will get over this. Where is the slide? Yeah, too fast. So what is happening is that we can. So here an example of that. So this one is a bomb in the toilet example. So if we have initially we don't know anything, then the possible word semantic, the initial belief state would be like all these possible four states. Whereas an approximation state is I know nothing. I have the empty set. Okay. And so I will skip this one in the interest of time, because I think that. And then now, if we wanted to define the transition function, I don't know where it. Did I? Oh, okay. So the transition function for possible words approach is that if I have the initial set of initial belief state, right? And so I define something like this. if I have a belief state S, then execute the action A in the belief state S would result in the empty state. That means that it's not executable if this action A is not executed in some of those states. Otherwise, it would be the conjunction of that. Right? And so it basically here in this, so we have 4 possible states. Flush is the action that can be executed in all of them. From here it gets to this one, and from here to this. So as a resulting state, so we have, if we execute the action flush, it will get to this one, and then if we had, so basically now the short space that we have in here is that we, instead of 2 to the n state, search for the plan, in classical planning we will have to deal with like 2 to the n. Okay? That, and for the approximation, okay. So let me. So in here we have I included here a few planning systems that for incomplete domains we have many of them. That are like so the action language they use to encode the problem is a little bit different. But so here we have like PDDL, we have like AR, which is in very compatible to the action language B, and that like action A. Okay, and one of the nice thing about ASP is that or CLP is that we could do parallel planning without any of the trade-off. We just, instead of 1 and 1, we just allow how many actions at least executed and how many. So we will have P and K, and so the lower bound and the upper bound. That many actions can be executed at the same time. We don't need to change anything. Right? So that's why the logic programming, DFK is one of the logic programming. It can do like concurrent action. So I will probably skip this one. I think that the later part is more interesting. So I wanted to give you an idea of how the approximation semantic is defined. The approximation semantic is defined in very, suppose that we have the initial partial state, so that's just a set of fluent literature that we know for sure to be true. So if we execute an action, then the direct effect of that action have to be true. Then of course the direct effect need to be, and then what we approximate is that we will just remove all the things that it possibly could become unknown, could become false, and that's something that we can have here. Say for example, in the bomb in the toilet domain, we know nothing. So we know nothing. Therefore, if we execute the action flush, it will become not clocked, right? That's all that we can. So there are some states in which we could have, what we could include is that the bomb would be disarmed, but we cannot make that conclusion. And as a result, execute the this sequence at the end. So we will only can conclude that it is clocked. We cannot. So here is an example of the approximation reasoning doesn't allow us to find the conformant plan that the design conformant. So it is incomplete. So here is a computation of that. So I will skip that. With static causal law, I think it even worse. Is that we cannot make the conclusion that allow us to do to make the conclusion. So we can extend the approximation semantic to allow to deal with the static causal law by having by including the direct effect and then trying to find the maximum part of the theory that could be calculated using this static causal law. And with that, we can here have two different approximations. One is like based on the idea of like a literal L is possible hold in the next state if one is that it is possibly to hold in the current state, and then it does not belong to the negation, the negative effect of the action, and then it also there is some statistical law that its body could possibly hold. In the other one, so we won't have this. We define this thing, and we will be able to show that this with this extension we can deal with statistical law rather effectively, right? And here, say for example, the domino example, we can get to like if we touch the intended result would be middle. And another idea of that, I will skip this thing, and it keeps almost the same results. But we can do it. What interesting thing is that we can only need to slightly change our encoding of the basic encoding of the ASP, and we can get the same result. So, for example, with the dynamic causal law, we will have like instead of, if you remember, so instead of hold here, we define the direct effect, and then we define a predicate of possible hold and deal with similarly, and then we use this last rule here to say that it is hold, and then it's not possible to be hold at its negation doesn't. It's not possible to hold at the next state. Then we'll have this one. So. What good about this approximation is that most of the time the approximation provides a trade-off for us to do things. So the trade-off is that we get to lower complexity. That's of course the price we have to pay, the incompleteness. And we have implemented quite a number of application of planner using the idea of using logic program, and we. It's very competitive with like some other CFF or Poner came at this time. The only downside is that it is incomplete. So I'm not. So what we do is we also try to use the approximation in a more traditional implementation using like source-based approach, and it turned out that it is very, very good. It's also competitive with other state of the art. Finally, I wanted to mention here that one of the things that we have, like B and PDDL, we have this. If we have the statistical law, B is much better to deal with comparing to the case of PDDL. So the next thing is that we can also like we will also extend the approximation semantic to deal with sensing action. And I think I will skip this part to give time to the other. The only thing is that I wanted to mention is that we just need to add to the action language one more syntactical item that like to declare that an action is a sensing action, and to say that if you is a sensing action that when we execute, we determine the value of the fluent literal in this set theta, right? So we call this new language called new, and we have, say for example, now we have two package, and we know for sure that exactly one of them it have a bomb in that, and we can do X-ray to determine which packet has a bomb, right? So that that we can have. So we will have no conformant plan for that, but we could generate the plan, the condition. So if we can, what we can do is that we can have this, and we define condition plan like this. So if I have an action, sensing action A with that determine the value of L1 to Ln, then after the execution A, we could have the cases. So there is a switch here that if it is true, then we execute that one and so on. We did basically extend the definition of approximation semantic to the case of the action theory with sensing action, and we implemented it in exactly in the same fashion as we have done before. One thing is that I wanted to show you this. Where that? I did remove it. I say sorry. So basically, now instead of having one parameter as a timestamp, we also have to add the branching factor. So the whole predicate would have 3 parameters. One is fluent, the other one is a timestamp, and the other one is branch. And that's all that is. So with that, I think that we cover the basic of answer set planning. So we will go to the hopefully more exciting application of the plan. So Marcello would do the schedule first.
So here we're going to look at how we apply all the techniques and technologies covered so far to the problem of scheduling. So first of all, from a high-level perspective, the problem of scheduling is a problem which we have several tasks, say T1 through Tn. For every task, we have a duration. That's the duration the task is supposed to take. And we're also given relations. We're given relations telling us which tasks should precede other tasks. Imagine you're building some widget and you have to first build its structure before you can paint it. So you have some kind of precedence between the 2 tasks. And also the overlap relation. So the overlap relation is the case in which you have 2 tasks that cannot occur at the same time. Okay, in any way so their durations cannot overlap. Their execution times cannot overlap in any way. So a way of representing this in ASP is by means of a relation duration, which assigns a duration to task Ti. A relation prec, which links 2 tasks and says that Ti should precede Tj, and then the non-overlap relation saying that Ti and Tj cannot overlap, and of course this is a reflexive relation, symmetric relation. Oftentimes in scheduling we're interested in finding schedules. The goal of the task is to determine assign start times for the tasks. And typically the additional constraint is that we want to minimize the total time spent creating these widgets or executing the tasks. So we want to minimize total span. So an example of a schedule is shown at the bottom here. Typically it's sometimes useful to represent schedules as lines over the number line. So each line corresponds to the duration of a different task starting from its start time. So in this case, if we have T1 with duration 3, T2 with duration 3, and T3 with duration 2, we might represent them like this with lines of different lengths. And if the start times are assigned in the way you see here, so for example, task 2 starts at time 1 and task T1 starts at 0, it's easy to see that T1 and T2 are overlapping. T2 and T3 are also overlapping, and T1 and T1 occurs before T3 entirely. In fact, it completely precedes T3. Like I was saying earlier, a task is an assignment of start times. We can also view that as a mapping of a set of tasks T to non-negative integers, which denote the start times, under 2 sets of conditions. So the precedence condition says that if we are told that Ti must precede Tj, then what you see here must be true, which means that Ti must be completed before Tj starts. This Di here is the duration of Ti based on the information given by relation duration. The second condition, or second set of conditions, if you want to view it as a condition for every pair of non-overlapping tasks, is that if you have a constraint saying that Ti and Tj must not overlap, then either the end of Ti is before or equal to the beginning of Tj, or the end of Tj is the same of or less than the start of Ti. So obviously there's no overlap at all. So you see here an example of something that is not a schedule, right? It's not a schedule because here we have that T1 must precede T3, that's fine. T1 precedes T3, but we say that T1 must not overlap T2 and vice versa, whereas here we have overlap of T1 and T3. On the other hand, here, this is a schedule because T1 precedes T3 and T1 and T2 are non-overlapping. Okay? So pretty simple definition. On top of that, we can define the span of a schedule as the difference between the maximum end time of the tasks in the schedule and the minimum start time of the tasks in the schedule, where maximum end and minimum start are defined in a straightforward way. So of these two schedules, we can see pretty easily that the first one has a span of 6 because we start at 0, we end right at 6 here, whereas this second solution has a span of 7. So as I was saying, oftentimes our goal in scheduling is that of minimizing the span. So in that case, we'll prefer the first solution to the second one. So how do we solve a scheduling problem in ASP? So it turns out that ASP is very convenient for solving scheduling tasks, and the intuition is that the definition of schedule and scheduling problem that I gave earlier is essentially it's constraint based, right? So it's clearly, easily translatable into ASP. So let's assume that we're given a list of tasks as a set of facts of the form task and some argument, a list of durations as facts of this form, and a list of preconditions and non-overlap constraints as we discussed earlier. A scheduling module, general purpose really scheduling module, except here we're going to cut some corners in the interest of time and space. So we're going to specialize it to the problem we're solving here. So a piece of a scheduling module for scheduling consists of a number of rules. The first one is shown here. This is a choice rule. Son was describing it earlier. So the goal is to assign a start time S to every task T. Okay, and the reading of the rule is for every task T, there must be exactly one start time assigned to task T, where the start time is some value out of the range of the domain of relation time, where we assume that relation time is established beforehand, and it provides the range of time steps that are available. So earlier we would have said that our time relation, the extension of time is 0, 1, 2, 3 through 7. Okay, integers, because as I said earlier, this definition of scheduling is based on the idea that we're assigning integers, in fact non-negative integers, to start times. Next, we want to, so this is a generate and test approach, by the way. Enrico was talking about it earlier, I believe. So the generate part is here. We generate possible start times. And then we start checking if these start times satisfy the constraints. So first we check for which tasks need to precede which other tasks. So we're saying that it's impossible for T1 to be required to precede T2, and for the start time assigned to T2 through here to be less than the end time of T1. Okay, kind of straightforward. The overlap constraint is essentially as simple. Just keep in mind that it's we have to take care of the symmetry here, so we have two rules. The first one says that it's impossible for us to state or to be told that T1 and T2 must not overlap, and yet to have that the end time of T1 follows the start time of T2, but the start time of T2 is after the start time of T1. So that's an obvious case of overlap. And we have it the other way around here by switching S1 and S2 in the comparisons. Finally, traditional scheduling, we want to minimize the span. First we need to compute the maximum end and the minimum start. To do that, we use a couple of convenience directives or operators, which are common in ASP solvers. These are not strictly necessary, but they are convenience constructs which improve performance of the solvers. There's a specific code behind them. So this one says that we're going to take the maximum of all the end times, so duration plus start time for every task T. That's going to be our variable, the value of M, and M is the maximum end. Similarly for minimum start, we're taking the minimum of the start times. And the span is calculated as obviously the maximum end and the minimum start. And then there's the minimize directive, which I don't think we've covered yet, where this directive which instructs the solver, again, typically supported by ASP solvers, it instructs the solver not only to find an answer set, but to find an answer set which minimizes, in this case, the value of S, value of variable S, where S is the span found in that answer set. So here we generate possible start times, here we make sure the constraints are satisfied, and here we make sure that the span is as small as possible. So I mean, it sounds great in principle, right? Is this practically viable, though? That's always a concern when you're dealing with a declarative formalism. You know, it's a great way to provide a specification, but is it viable for practical applications? And so for that, I actually ran a small experiment for this tutorial. Sort of put together a few things from past experience. So in this small experiment, I took 5 tasks, and I considered different durations for these tasks. The durations were randomly assigned over values ranging between 100 and 200. I considered different trials. So in the first trial, the maximum task duration was 100, and the duration for each of those 5 tasks was randomly generated in the interval between 50 and 100. And then I increased the maximum duration by 10 units at a time, and I always randomly selected the duration of the tasks in the range mu over 2 and mu. For preconditions, for precedences, I randomly generated the pairs, randomly generated 30% of the pairs. And I did not include overlap constraints, and I also did not do spam minimization. So a very simple kind of task, not really realistic. And yet, execution times, as you see here, were not terrible, but if you consider the simplicity of the task, they were not great either. There's a couple of things that are worrisome. The first one is we have only 5 tasks and very simple constraints, and yet it takes us 11 seconds to find the solution to this problem. There's many solutions, or many start times that you can assign are probably pretty decent solutions, and yet it takes us 11 seconds. And then the second thing, which is problematic for practical applications, is as we increase the length of the tasks, we're not really complicating the problem, right? If the precedences are still randomly generated 30%, and by the way, I had 5 trials for each of these, and I'm averaging over all of them. The duration of the tasks intuitively doesn't cause the problem to become more difficult, and yet you see a time increase, right? So, yes, it works. It's great for prototyping, which was one of the reasons why we always advocate for the use of ASP. For practical applications, maybe we can do better. Yes?
May it not be that if the tasks are larger, the overlapping is more probable, so it's more difficult to, the complexity may actually...
It might, but we don't have overlap here.
Okay.
Right, so the precedences are there, so maybe there is a little bit there. But most of all, this is due to the grounding, right? We have a larger range for time. So the start times, here the solver needs to worry about only 100 possible start times. Here we're going all the way to 200, so it's a wider range. Intuitively, what we want is not to worry about the specifics of the numbers. These are just numbers. We should be able to crunch them easily. And so, Q in CASP. So CASP has the ability of combining the qualitative declarative aspects of ASP plus the essentially number crunching of constraint satisfaction. So we can show here how using CASP, elaborating the solution in order to use CASP instead of just ASP helps us. So obviously we use CASP instead of ASP. Whatever qualitative parts of the problem, we're going to encode in ASP, and then the numerical parts are going to we're going to be encoded using constraint solving, but still embedded in ASP, encoded as ASP statements. So what does this boil down to? We have the same input as before. Generating start time changes a little bit because this is arguably the constraint satisfaction part of the problem, right? So we're going to declare a set of start time or variables representing start time, one for each task. We can just out of convenience, we don't really have to, but out of convenience we can state that the range of the variable, we can state the range of the variable right here, and length is some externally provided parameter. And then the key is here, we have to we have to specify that the start times have to be assigned in a way that's responsive to the durations. That's done by means of a global constraint. Remember I mentioned global constraints 2 hours ago, more or less. There's a global constraint in constraint satisfaction which is specifically geared towards scheduling problems. So there's specific algorithms built in. And this one takes care of very efficiently assigning start times. Incidentally, here the list notation, I'm not going to go too much into it, but the list notation here is something specific to the easy CSP. There's slightly different variations to the syntax in other flavors of CASP. The idea is if st is a variable, an expression st/1 in square brackets means this is the list of all variables of the form st with rt1. Okay, so it's the equivalent of this list down here, and if duration is if the first label is a predicate, as it is in the case of duration, then duration/2 says take all predicates of the form built from all atoms built from duration and of rt2, take their last argument and build a list with those arguments. So in the case of duration, the last argument is the duration of the task. So we're going to have a list of durations still ordered by the corresponding tasks. It's a little bit more complicated than that to properly explain the semantics of the list, but the list notation, but I hope it gives the idea. Then we have to ensure the precedences. So that's done, that's again part of the constraint satisfaction problem. All we need to say is that if, let's see how the ASP component and the constraint satisfaction component are linked. We're saying if we know that T1 must precede T2 and the duration of T1 is D1, then, and what you see in here, this is a constraint from constraint satisfaction. So then it is required that this expression is in the constraint satisfaction problem, where the expression says that the start time of T2 must be after the end of T1. Non-overlap is handled in a similar way. We use disjunction here, disjunction within the constraint satisfaction problem, which is supported by several constraint satisfaction languages and flavors of languages. And so if you take all that and you run it, you find something that's a lot closer to what we would have expected. So the maximum task duration has no effect on execution time, essentially no effect, negligible effect. And the other aspect is this is a small 5-task problem with very little constraints on it, and it's solved very quickly. Right. Now you might be wondering though, so basically all of this is really constraint satisfaction. There's no ASP. I mean, yes, the language is ASP, but what's the use of ASP? Why not just use constraint satisfaction? So a few years ago, I was working at a company, and I was in charge of workflow automation. And so that's in fact where EasyCSP started. So we had, we were dealing with the automation of the print production. So imagine printing books or magazines. There's print shops, big, large print shops with lots of devices, and you have to figure out how to use those devices properly, you know, how to sequence the operations. It's essentially job shop scheduling with a few twists. In fact, major twists, because it's not just scheduling, it's in fact also a planning problem, but we're not going to worry about it right now. If you just focus on the scheduling problem, you have the ingredients essentially of traditional job shop. You have multiple job phases. Obviously, earlier job phases must occur before the later job phases. For example, I have to print the big press sheets before I can cut them into smaller parts. I cannot do it the other way around. So I have to, this intuitively will give me a precedence between tasks and also non-overlap. I have to finish printing before I start cutting the pages. But the twists, well, the twists deal with the fact that in practice, people were handling devices that might fail at times. in the middle of a job. They were also dealing with cases when a rush order might come in and people had to respond without disrupting the existing production, the current production. So that's where the ASP part of CASP becomes useful. So first of all, the job shop scheduling part of the problem is solved in a very similar way to what we've seen before. Just a few nuances to handle the fact that we have multiple device types and the same job will run on multiple device types at different times. So the same job, say this book, will first have to be printed, then have to be cut, and so on. But this is a tiny variation. Precedences are handled in just like we've seen before. Did I skip something? No. Okay. The interesting part is the incremental updates. So let's say that we've already computed a schedule. In fact, it's being run, and all of a sudden we are asked to add new jobs to the mix. Some of these jobs may be rush jobs, so they have to be executed as soon as possible. But if we're already running something, we cannot stop. We should keep running that. And jobs that have already run should be completely ignored. They've already run. We don't want to rerun them. So let's say that the current schedule is represented by these three relations. So current start of each job, current device on which each job is running, device type really, and the current time, what time it is right now with respect to the existing schedule. So all of this describes the current schedule together with the current time. So how do we make sure that we introduce new jobs without causing and do not cause any disruption to the currently running jobs? First, we can say that based on these relations, we can determine which jobs have already started. That's easy, right? We check the current start, check the current time. If the current start is before the current time, we're done. Those jobs intuitively must not be rescheduled, right? They shouldn't be touched. Their start time stays the way it is. That can be done in ASP easily as well, right? With a rule like this. And just to be on the safe side, out of experience, it's useful to say that there may be exceptions to this rule. So we turn it into a default where we say, if I have no reason to believe that this job is abnormal with respect to not rescheduling things, we're going to say that we're not going to reschedule it. But we may have exceptions. Finally, almost finally. So jobs that must not be rescheduled based on this rule, they will be assigned the same start time that they already have, and in fact even the same device that they already have. I'm not showing it here. So we are injecting into the constraint satisfaction problem this constraint. Jobs that, and unfortunately it's cutting down here, but the jobs that can be rescheduled, that do not have to be kept the way they are, their start time is set to the future, right? We don't want anything in the past. So we're injecting a different constraint into our constraint satisfaction problem. Okay, so that allows us to add new tasks in the mix without touching whatever is already running. However, what if a device has failed? What about the jobs that were running on that device? Well, they were running, so I shouldn't touch them, but production has failed, so I should definitely move them to some other device. I cannot have them sit there and wait. So again, ASP, and in particular ASP's non-monotonicity, becomes very useful here. Recall this rule where we decided what should not be rescheduled? This was default, right? Well, jobs whose production has failed definitely are an exception to that default. So if a job has already started and production has failed, then that job is abnormal with respect to the rule that it shouldn't be touched. Okay? So for those jobs, we conclude that they're abnormal. Therefore, the system will not conclude that they must not be scheduled. They can be scheduled or really rescheduled in that case. Therefore, this is not new. This we've seen before. This rule applies to those jobs, even though they were already scheduled. Right? It is not the case that they must not be rescheduled. Therefore, they will be rescheduled. Therefore, their start time, is now in the future. It used to be in the past. They had already started. Now it's moved to the future. So here you see, this is sort of the culmination. You have heavy non-monotonicity in here that allows you to decide what should or should not be rescheduled based on partial information that you may have. And if you add new information, things get reevaluated seamlessly. And at the same time, this feeds into the constraint satisfaction aspects of the problem. And so this summarizes. So in green, you have the aspects of the encoding that leverage ASP's non-monotonicity. In blue, you have the constraint satisfaction parts. Okay, and of course, there's a lot more rules than this.
10 minutes to talk about a few other applications. And I think that when we prepared the presentation, we were thinking of like 4 hours. But I think that so now I will just very briefly introduce you to a few applications that we have been using answer set programming to solve it, and with a very interesting result. So probably I will mention these two and then leave the other one. The last one is very interesting because it combined constraint logic program together with ASP to solve the problem. But if you are interested, maybe we can communicate offsite. So I wanted to let's just move on. So here. The first application is the code recognition design, and it is very related to the code recognition problem. So let me start with the code recognition problem first. So assuming that we have an agent that's sitting here, and then we know that it is going to one of these 3 locations, and under the assumption that the agent acts optimally. And we are interested in identifying what is the code of this agent. That's the code recognition problem, right? So, and it is a special form of the plan recognition, and there are many applications with that. And I think that Milin Tamber will talking about that in the main conference a little bit about that. But so suppose that we observe this agent and it goes to the left, for example. Then because of the condition, the assumption that it acts optimally, we would be able to recognize that the code of the agent would be this one, G1. It goes to the right, we only know that it is like G2 or G3, but we cannot distinguish between G. But if go up, then we cannot make the distinction. So now, in code recognition design, and that's problem invented by Karen, who was trying to watch, but I think it's too far away. So see, the idea was that so if I wanted to do this, if I want to recognize the goal of the agent, what happens if I block some of the action that the agent can do? Then I could probably recognize earlier. So we could modify the planning problem so we can recognize the code as early as possible. That's the code recognition design problem. Now, and so they introduced a notion called worst case distinctiveness. Okay, what is worst case? That is the maximum number of actions that the agent can execute before revealing the code. So if the worst case, this one is equal 1, no, because it can move here and still we cannot. But if we go like it is 4, then we will be able to recognize. So the problem, let's say for this particular example, the worst case distinctiveness is 4, right? So now, how do we find And how do we find them? So here, say for example, if we can block, if we block the action, this action, then it can only either go left or right. So, and then with the 3. So here, if we block this action and that action and that action, so this action, that action, we can reduce the WCD to 2. Right? So that is how the thing is. Now the problem is, how do we compute this WCD? Okay, and so what we can do is that we can we introduce an integer k and identify. So now we wanted to identify the set of k actions so that the WCD of the problem without this k action is smallest, right? And we did we kind of so what Karen and the other author will have done is that they they basically develop algorithm and implement it on top of a planning system. So what we're trying to do is that we're trying to see whether logic program can be used to do that. As you know, that computing the minimum plan or the optimal plan given the goal is easy. We can do that already. So now what we can do is that we will represent the goal recognition problem as a logic program. And then we try to solve that. Basically, that's how we solve the problem. And the general idea is that we can, there are two possible solutions. One is that we can represent the problem as basically a QBF and using the answer set program to do that. The other one is that we get a set of action K and then by introducing this block at most K action and then do not use it action that are blocked to generate the plan, right? And so we will try to identify the best answer with that. So that's how we do. And I will. So here is the idea of like the WCD. So basically, we can represent the WCD to this formula. I'm not bothering you with explaining that, but basically, it says that trying to find the common prefix of the two minimal cost plan X and Y. So where pi star G is the optimal plan for G. So we have two goals, X and Y, and then we're trying to find the maximal, the common prefix of these two plans. So, and then the whole problem can be formulated like by using this. So trying to identify that one. And we can basically encode this, there is techniques that we can encode the WCD, so the QBF as a logic program and then feed it to the solver and solve it. Okay? And we did do I'm not going, so we did make the implementation. And we also do the other one, the standard one, that calculate the, given a K, find the blocked action and that, so we have basically two encoding, one for this one, and we did compare with what Karen, so the system, the PR, the system of the author. So basically, we see that the two approaches do pretty well comparing to the state of the art, and so this is this is the case of blocking one action. This is the case of blocking two actions, and you can see that like here we have like it's pretty good here the results. So I think I could skip it. So these are all the instances of the benchmark that is used by Karen and so this shows that answer set programming could be pretty interesting in certain applications like that. And I have 3 minutes to talk with you about. So this is something quite interesting in the. This is the problem that we call generalized target assignment and pathfinding. So to give you an idea, so this is the. How many of you are aware of this Kiva system by Amazon? Yeah. So that's the one, right? So in this, so we there are a lot of work that have been used in multi-agent pathfindings. But the Kiva system added another extra level to that. Like, not only you have to find the path for the multi-agents, but also there are constraints that like the agent have to visit a sequence of checkpoints. So not just only go to one point, but it's going through the whole checkpoint in order sequence. So and basically the problem is so that planning for one single agent is not too bad, but planning for multiple agents, there are problems. Let's say we need to avoid this kind of strain. Like if one robot is here and the other one, they cannot swap in one step. And then so if one robot stops, the other cannot like bump into the other. So that's basically the idea. And the general idea is that we wanted to have like minimum span or minimum total cost, and some if we associate cost with that. Now, so what we have done so far is that we can easily encode this problem in ASP, where basically previously we have this predicate, say hold at LT to say that a robot is at location L at time T. Now we have to say that okay, we have to attach to the like say the robot R is at the location L at time T, and then we have also to have to specify the connection between the action execution and the robot, the agent. So we have this kind of thing. So agent R executes the action A at the time T, and then encoding the rule to deal with constraints. So very simple. And also, like to enforce the list of checkpoints, very simple to do because it basically represents a temporal constraint. We can easily edit that, like as I have shown you to in the planning with preferences. We can enforce that. Now, the interesting part is that if we just put this thing into the ASP solver, we will not be able to solve because of the number of the robots and the map is large. We will not be able to solve the very simple problem. So we will not be able to solve the optimal solution compared to what Sven, Koenig, and Hangma have done in this. So what we can do, what is interesting is that we found out that we could use the power of modeling in ASP. Like what we can do is that if we abstract away the constraint, the map, and solve the problem, we can do a lot of we can scale the problem quite large. So in the idea of abstraction is like this. Suppose that we have the map like this, and the connection is like that. The connection is like typically that's how it is constant. So what we do is that we basically collapse all the point into like first we collapse this thing, that thing, and that thing into one single point. And then, so we reduce it into that. And then the next step, so we can basically clearly identify this group of nodes to make single node like that. So basically, from a large map, we can reduce it to. And the interesting part is that all of that you can do that automatically using some very simple ASP rules. So the first one, for example, like basically you can group the point based on their connectivities, and this connectivity can be calculated using using aggregate through in logic program. And so we get this simplified map. We do the planning in that simplified map, and we then basically regenerate, so decouple the plan after that solution. And with that, we can reassemble part, and from like we can originally with the original code we cannot solve. But if we added that abstraction, we can solve the problem with quite large number of ideas. And the trade-off is that so far we haven't been able to find the optimal solution though. But like what we learned from the Kiva robotics, that they also does not very worry about the optimality of the solution yet. So that's something interesting to share. So with that, I think that I probably wanted to stop here, unless if so. Just to mention that we also use ASP in distribute constraint satisfaction optimization in decode. So and here's quite interesting is that with the power of modeling of ASP, we can achieve quite a bit of scalability in domain where the set of hard constraints are like it's large, and the domain size is also quite great. But I will skip this part. I think that the interesting part is that we do have in this case have to have the connection between ASP and basically Prolog to drive the implementation. So I will skip to the probably to the conclusion, so that to say that basically we have managed to introduce to you a few flavors of logic programming and discuss its application in certain applications. That is, so thank you very much for staying so long. I hope that if you have any question, or if you wanted to have the slide, we can send you to the slide through email. If you any question, comments? Yeah.
It may be a naive question, but I've come across some general definitions of semantics for logic program, but I don't really know why the ampersand semantic is the semantic of choice in the logic programming community. So could you probably elaborate on that?
No. I think that at least I cannot tell it. Maybe Marcello have a different opinion here. But for one thing, is that that is true that there are different semantics, and the two most frequently used semantics are the well-founded semantic and the answer set semantic. But well-founded semantic is very skeptical in a way. It's very skeptical, and answer set semantic, I think it is useful for different reasons, especially for problem solving. So you can see that, let's say in the example I showed, if you use the well-founded semantic, you would not be able to solve problem like all the problems that we have, because well-founded semantic require that something is true in basically it's true, given the program. But if, say for example, in the graph coloring problem, one node can have multiple color in different answer set. So if you ask for the question whether the node 1 is red, then the answer would be false with respect to the well-founded semantic. So you would not be able to do that kind of thing. But well-founded semantic, for example, is very good for say query answering system, where you really need to have an answer that is true. You have a knowledge base and you want to know that whether the statement is true or false given the knowledge base, then well-founded semantic may be a better choice for certain application.